Okay, this hour we'll talk about two different analysis methods to analyze malicious software. Okay, the first one is called static analysis. Um, static analysis is some kind of analysis method of computer software. Once you collect the software executable file in Windows, is the exe file, then you can use any method you know to analyze this specific binary file. But the only thing that you cannot do is to execute it. Okay, so that is the reason why it is called static analysis. You can only analyze the binary itself, and if you want to execute itself, then it becomes dynamic analysis. Okay, so for dynamic analysis, you can execute the executable file in usually in a quarantine environment. Okay, and you may want to use a very old version of Windows operating system and execute the software and try to set up a lot of different monitors to observe what is the interaction between the malicious software and the operating system. So basically, there are two different types of analysis method. Okay, so first we'll take a look at the static analysis, and then we'll talk about dynamic analysis. Okay, we focus on Windows malicious software. So basically, the Windows executable file is called PE file. Okay, portable executable. It is a format made by Microsoft. Okay, so we can see that it has a very complex format. Okay, and right here, okay, because in the early days, before we have Windows, okay, every executable file should be executed on DOS operating system, right? So now, even if we don't use DOS right now, our executable file still has DOS header, okay, and there should be a signature 5A 4D, okay. These two specific bytes specify it is a DOS file, okay. And then there are some other complex things, and of course those are several different sections, and each sections specify, for example, what this executable file is compiled for. For example, this executable file can be run on Intel A03 A6 machine, or it can be run on a 64-bit machine, or it can be run on ARM CPU. So it will specify what kind of machine it can be run, and when it is compiled, or a lot of different information in these sections. Okay, we will not go over every detail because it is too complex. Okay, so if you're interested in how a PE file is constructed, maybe you can take some course like compiler, or course related to CPU. Okay, so and of course in Python we will have a very nice tool to help us to decompose these P files and help us to analyze the P files. Okay, so that is P files. And one important thing is that when we compile our Windows file, for example, you write a C# or C++ program, and you can see that there will be some concept called section. Okay, your main function may be compiled into one single section. Your function, okay, self-defined function, can be compiled into another function. Your global variable will be compiled into another section. Your resources like the icon, of your Windows executable file will be compiled into a section. So there will be a lot of different sections and stored different resources, different codes, different variables. Okay, so that is the concept you need to know. So here we have a example right here. We download a well-known that is a well-known executable file called PuTTY. Okay, it is used for SSH communication. Okay, so it is a good, it is a benign software. Okay, we downloaded it from the network, from the internet, and it has two different versions. Okay, we have 32-bit versions of PuTTY and 64 version of PuTTY. Okay, so here we have two different executable file. Okay, so before we use Python package to analyze these two P files, you can try by yourself. Okay, but I strongly recommend you simply just use the well-established package to analyze those P files. You don't have to write it by yourself. Okay, but we can make some practice right here. So one of the way to identify if a file if a file is a P file or not is to check against its sub file name, right? But you know it make no sense because you can easily change your file name. Okay, it is not necessary to be a P file if you rename your file as a .exe file, right? So there's another interesting thing study, and since I say there's a signature right here. Okay, it is 5A4D. Okay, actually it is MZ in binary way. Okay, it is ASCII character MZ. Okay, so you can simply just I open the file and I read the first 2 bytes and check if it is MZ. If it is, then it is a DOS file. If it is not, then it is not a DOS file. Okay, you can write your parser by yourself, but I don't recommend to do so. Okay, and again, as we mentioned, okay, there's another signature right here. Okay, there's another signature right here. You have to first check against the first 2 bytes in the DOS header and check against a special pointer right here. Okay, the pointer is located as 0x3c, and the value in this address, it points to the very first byte of your next header, which is right here. And there is a signature 50450000, and it specifies it is a P file. So again, you can write your own parser. Okay, it's very similar to parse or packet. Okay, we have talked about how to parse a we have talked about how to parse a packet in other class, right? But that is how you use struct unpacked to read those information. Okay, that's just some examples, but I again, I don't recommend you write your own parser. Okay, it's very easy for you to make some mistake and to do wrong, to make a wrong parser. Okay, that's just one of the example. Okay, so if you're interested in how to write your own parser, you can check the code, but we can use Python packages later. Okay, and again, you can print the P files by using hexadecimal way, right? So we can see that here's the here's the first signature and here's the second signature right here. Okay, And again, before you continue our course, okay, make sure you read this video. Okay, we prepare a video for you. It demonstrates how hash function works. Okay, how hash function works. So make sure you understand how it works and come back later. Okay, so I wish you read the hash video. Okay, so the next thing is that we use the PuTTY exe file as the input of the hash function, and we generate its MD5 value and its SHA-256 value. Those are hash values of this specific executable file. If you change one bit in this executable file, and this hash value will be changed dramatically. Okay, so so sometimes we use this hash value, MD5 value, and SHA value to represent the malware we collected. Okay, so that is this one. And again, okay, we'd like to talk about interesting concept called signature. Okay, so so here it is. Okay, so if you want to do electronic signature, okay, that is how it works. Okay, we change it, we erase all things right here. Okay, so here we have a document right here, which is the data. Okay, it can be any binary data. It can be a document, it can be the exe file, it can be an image, whatever, as long as it can be represented digitizedly. Okay, so that is the data we like to protect. So in order to protect this data, we need to sign this data. Okay, so the very first thing is that we use the digital data and pass it through a predefined hash function, and so that is the data, right? So that is the hash function, and we have the hash value right here. Okay, in order to do digital signature, okay, we need to prepare something. Okay, the first thing is that private key, and the other one is public key. As a signer, you need to have two keys. Okay, they are a pair of keys. Those two keys, they have a very complex mathematical relationship. Okay, if given a public key or a private key, we can identify if they are a pair of keys. Okay, we have some way. Okay, we'll show you later. Okay, so after that, okay, since we have two keys and we have two programs, okay, one of them is called encryption. It is a function. Okay, it is a function. And again, for this encryption function, you need to provide a key, and that is a private key, right? And the thing you like to sign, and right here we sign the hash value, not the digital data, that big D. We sign the hash value. Okay, so that is the signature. We use your private key and a predefined encryption function to encrypt your hash value. So that is the signature. So after that, okay, we use the digital data right here and the signature right here. So that is the signed data. And you can pass this signed data to your friend. Okay? But when you send your signed document to your friend, you don't know if that signed data has been modified or not. So when your friend receives this data, okay, it is not necessary to be the authenticated one. So we write it D prime right here and the signature prime here. The signature might be modified by the hackers or something. The digital data, big D, may be changed by the hackers or not, or something that which we don't know. But it's okay. When we receive this signed data, we can further verify if it is modified or not. Okay, so we have a D prime right here. We have a signature prime right here. And again, we use the same hash function, okay, to produce H prime. Okay, the process is exactly the process right here is exactly the same as it right here. Okay, and at the right hand side, okay, we have another function which called decryption function. Okay, and given the public key and the signature, because the key of your private key and the key right here, your public key, they have a very strong mathematical relations. Okay, so the result would be a hash double prime. Okay, we put it right here. So you can see that the operation right here, okay, that is encryption. We use the private key to encrypt your hash value and get your signature. And at the right hand side, we use the decryption function and use the public key on your signature, and we can get the hash value. So at the end, we need to, as long as these two values is the same, and we can guarantee that your digital signed document is not modified by any others. Okay? If your digital document has been changed, okay, and then the corresponding hash value will not be exactly the same as this one, hash double prime, right? If your signature has been changed, okay, and then your hash double prime will not be exactly the same as hash prime. If both of your digital signature and your document has been changed by the hackers, then you can see that since the hacker does not have your private key, so using the corresponding public key will decode the signature, and the result will be some random value, because the signature right here is not generated by using the private key. Okay, if the hacker uses a random signature or random document right here, and you use the correct public key to decode the signature prime, and the result will be some random values. Okay, it is a little bit complex, but that is how it works. Okay, so as we can see that you can still download the signature of your PuTTY executable file from the website, and you can see that we can download the keys, we can download the signatures, and we can see that okay, this P files has been signed by the author of this program. So sometimes when you download a Windows exe file, okay, I think most of the exe file is signed by the by the authors, and that makes the P files more safer for you to use them. Okay, because hacker will not sign its malicious file, right? And once you have the hash values right here, okay, please take a look at this the website called VirusTotal. Okay, VirusTotal is a very a very useful tool for us to okay, okay, let's try again. We can input the hash values generated from here. So this one, I think. Okay, I cannot copy this. We can simply just search some random. Oh, sorry, I should. Oh, we cannot search the name right now. Okay, I want to know, see if we can copy the MD5 value right here. Maybe not. Okay, that's okay. You can copy copy some MD5 value. Okay, we will show you later. Okay, and check it against with the VirusTotal file. It gives you some information about this malicious software, including how many different antivirus engine can detect such malicious file, or what is the name of this file, what is the static analysis result of this file. Okay, the next we'll have to introduce is the P file, which is the static analysis tool, okay, in Python. So simply just install it, and you can simply just execute some built-in function, okay, including what is the machine of this P file. Okay, 332. Okay, so you have to take a look at this document. Okay, Microsoft has a very well-established website which tells you how to decompose a P file, and what is the field of each sections. So there'll be a lot of different values and tables you can refer to. Okay, so for example, right here, it indicates it is 332, right? So you can check against it with this value in this table. Okay, so again, there will be a lot of headers in this PE file. Okay, so you can check against. Okay, and again, it can print all the sections. So I have section names and some other sections, and each sections stores certain information about this executable file. And the text section, it is the main function of your executable file. Okay. But there's a interesting thing is that most of the time when you distributed your PE file to the public, okay, sometimes you may have a lot of files. For example, you have an external library, you have an external image, so your executable file would need these different files, right? So there's a technique called packing. You can pack your files, a lot of files, into one single execution file. That's called packing. And some malicious attackers, okay, they will use different packers to repack their malicious files. For example, there's one thing. Okay, we have DOS headers or P headers, and we have a TXT file headers. And as I mentioned, your main function will be included in the TXT section. Okay, and maybe the main function, it is a zip function, or it is a decrypt function, or it is a compressed function. The real functionality will be packed in the later section, and this main function only unzip this section, this purple section, decrypt or decompressed this purple section, and after decompress, after decrypt, after unzip, your program can be run. Okay, so that is called packing. Sometimes malicious software attackers, they write their own attack programs, okay, and when they'll pack the attack program in this purple section. Because this part of code has been compressed, has been encrypted, so it is not that easy for the researchers to find out if it is a good software or it is a bad software. Okay, so sometimes they perform packing. Okay, and again, since they perform packing, so we as an analyzer, we can perform unpacking. So we install the UPX software, and here we packed our PuTTY32 and generate a packed file, PuTTY32 packed. Okay, and then as we can see, it somehow has been compressed. Okay, and the section name changes, okay, to UPX0, UPX1. You can observe this value. in the P file. Okay, and you can see that the MD5 file, since we know we changed the appearance of the P files, right? So the MD5 value changes as well. And you can see that after the file has been changed, the signature is no longer valid. Okay? So in order to identify if a file is packet or not, okay, there are some resources. Okay, we have to download some database, and those database can help us to verify, okay, some file, the file we just packed it is packed by this software, so that you can understand, and we can see that the section name changes. So that is the reason how that is how we identify if a file is packet or not. Okay. And again, to analyze a malicious, to analyze a software, we can simply just print the every function it invoked, so that we can use this. Okay, please spend some time to take a look at this code. Okay, we can print every function name it code. Okay. So an idea is that do you believe that for malicious software, the function code it codes is a little bit different from a business software? If you believe so, you can create a neural network or a logistic regression detector, okay, to differentiate the function codes coded by malicious software or business software. Okay. The next thing is that there are some strings that you can print out from the P file. Okay, so that is a demonstration. Okay. The next things I would like to talk about is what if we cannot specify it if a file is packed or not packed, or is encrypted or not encrypted? We can simply just count. Since we know that the binary file, the binary file is a byte, right? It's a byte array. For every byte, okay, its value is between 0 to 255, right? We can count how many different bytes a P file has. Okay, for example, 0 means that byte is 00. 255 means the byte is FFF. You can see that, okay, the distribution of the byte counting, okay, looks not even. We can see that some area, some range, okay, it has a higher frequency that those bytes appears in the P file. Okay, and we can see that is the ASCII, the range of ASCII, printable ASCII characters. Okay, but if you take a look at the packet file, because most of the byte has been encrypted, compressed, and or zipped it, so you can see that the distribution of this byte count will be more evenly. Okay, so that is how we check if a file is packed or not without using any database. And again, we have another tool which can help us to the assembly. So that is exactly how CPU execute our P file. Okay, you can also use this information to distinguish binary software and malicious software. Okay, we'll skip the fuzzy hash. Okay, we stop right here. So that is the first part. Okay, we can use a lot of different packages, tools to help us to decompose the information that we can retrieve from the PE format. And if we do believe that benign software and malicious software, they do have some differences in this specific format, and we can create a detector, right? Okay, so that is the first part. That is the static analysis. Okay, so the next one is dynamic analysis. That means we execute the P file in a quarantined window or old Windows operating system, and we observe what is the relationship, what is the interaction between the P file and our operating system. So please take a look at these things, and here's one of the example. Okay, that is the example I would like to show you. And you can see that specific malicious software, okay, in VirusTotal, you can observe, okay, there are 47 different detectors, and 27 of them believe it is malicious software, and it gives it some different names. For example, low money, cryptic, or something. And of course, there are some detectors, they don't think it is a malicious software. Okay, and take a look at the details. You can see that there are a lot of hash values right here, so we can uniquely identify which malicious software it is by using the hash value. Okay, and including when it is created, when it was being when it has been analyzed, and what is the signature information. You can see that it is signed, but it is signed by some malicious entity, which is called LLC mail RU. Okay, usually if a software is signed by some big company, that will be signed by Google or Microsoft or some large company. Okay, and here's the information, and you can see that it has a lot of different sections, and here's the size of each sections. Okay, and it calls a lot of different function calls from different libraries, and we can extract those information from Python, from the PE file, from package. Okay, so basically that is okay. And again, as we mentioned before, when we perform dynamic analysis, we need to execute it. So we set up a monitor in our experiment environment. We can collect a Windows API calls it invoke when it has been executed. Okay, so that is the Windows API calls it calls, and we collect those information as its behavior profile. So that is what I would like to analyze. Again, if you believe that the malicious software and the benign software, they do have different patterns of those calls, and you can design a neural network or some other machine learning algorithms to distinguish them. Okay. So here's another example provided by my lab. Okay, and it says, okay, that is a timestamp. It invokes this code with these parameters and this return value. At this moment, invoke this code with these parameters and its return value, and so on and so forth, so on and so forth. It has more detailed information about the execution. Okay, and again, you can design your own detector. So we have example right here. Okay, we have example right here. Um, it has 4 different classes. Okay, so the simplest way to analyze this is simply just count how many different cores a sample has. So that means this specific sample 565, it in its execution sequence, okay, one of them is EXECVE, okay, and 3 of them is BRK break. And of course, it is I think it is just one of the simplest way to analyze malicious behavior, okay. But as you know, it is just simply just count, okay. It's simply just count, and you can use any algorithm, any tools to help you to perform classification. As we mentioned, we have 4 different classes right here, right? So you can achieve 95% of accuracy if you apply neural network, okay. And by using this, you can also perform hierarchical clustering, okay, and you can plug them into a 2-dimensional space to observe different clusters, right? But one of the things I'd like to mention is that the original data is a sequence of event. But when you transfer the sequence of event to this table, this table does not contain any time information, right? So if you ask you, if your malicious software asks you something like this one, ABC, 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 if a benign software that called ACB, 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 and in this counting table, the value is the same, right? So you cannot distinguish ABC and ACB by using this table. So that may be wrong to do so. So in the next course, we'll talk about how to deal with sequential data. Then we have to consider different sequences. Okay, so we stop right here and we continue next hour.